All right, I want to just go over how I got all the answers on the practice exam. So for the first one, we're talking about packing. So if it was 1 atom per unit cell, I know that would be called simple cubic. For uh, 2 atoms per unit cell is body center cubic. Remember, that's the corners plus 1 in the middle. And then 4 atoms per unit cell is face center cubic. That is the corners plus 1 on each face. So since this is asking about 4, it must be face centered cubic. For phase diagrams, I know that when I look at the low temperature, high pressure side of the graph, that would be the solids. And when I go to the high temperature, low pressure, that's gas, and in between is liquid. A is right in the middle of the liquid section. For number 3, I'm looking at a straight line and I see the x-axis is 1 over the concentration, or the y-axis, sorry. So then I know that corresponds to second order. Remember, it would be a straight line if it was just concentration, if it was 0th order, and a natural log of concentration if it was first order. But this is second order. It doesn't tell me any dependence on y at all, so it must just be the second order in x only. B. Okay, next up, as soon as I look at this, I see an oxygen directly bonded to a hydrogen. I know that means it's got hydrogen bonding, which means it has all 3, dispersion, dipole-dipole, and hydrogen bonding. For this next question, it shows me the units of the rate constant, and that is enough for me to determine the order. Remember, seconds in the denominator would be for first order. If you're not sure, just pick one and try it and see what the units would look like. So I know it's first order, so that's what I picked, and I wrote rate equals K times the concentration of A. Solve for K, I get rate over the concentration of A, molarity over second divided by molarity, cancel, and I've got just seconds on the bottom. For this next question, I see the first one says no change in boiling point. I know there's going to be a change in boiling point. And then the rest are like about boiling point, melting point, and freezing point, or vapor pressure. So I know vapor pressure always goes down. I know freezing point always goes down, and boiling point goes up. So the boiling point won't go down, and the melting point or freezing point won't go up. Remember, freezing point and melting point are the same temperature, but the vapor pressure would go down. For gas solubility, when it decreases, it would decrease when the pressure decreases, which is not an option, or when the temperature increases. Remember, that's opposite of a solid. Increasing temperature decreases the solubility for gases. For the next one, I have some ionic compounds all with the same concentration. So the only difference here is the I. So I just want to look at how many particles they each separate up into. And I would get 4 for Al, aluminum, and 3 hydroxides, 2 for K and Cl, and 3 for, I can't see my hands in the way, the Na2 and SO4. All right, and then finally, I'm looking for high intermolecular forces. I see NH3 has a nitrogen directly bonded to a hydrogen, so it would have hydrogen bonding. It would have then the highest boiling point and the highest melting point. All right, for the next question, it's a kinetics problem, and this is given in terms of partial pressures, but I'm going to write it all in terms of concentration the way we did it in class. It doesn't matter. It's just a way of thinking about how much we have in a certain, like how much it changes. So I wrote C6H6, but I think we're actually asking about 14, and how that relates to H2. So I'm just going to write this rate expression as it corresponds to those two things. So C6H14, it would get the negative sign. The H2 gets 1 over 4 because of the stoichiometric coefficient. And then the thing that they gave me was how the concentration of the C6H14 changes over time. That is a negative 6.2 times 10 to the minus 3 atmospheres per second. There's also another negative sign there, so that makes it positive. And then I just want to solve for the concentration of H2 over change in time, and so I would multiply both sides by 4 to cancel that. And so I get whatever 6.2 times 10 to the minus 3 times 4 is. And to 2 sig figs, then that'd be 0.025. And then the units would be the same as the units. I missed a 0 in here, but the units would be there we go, atmospheres per second. All right, next up we have a vapor pressure problem. Remember, vapor pressure depends on the mole fraction, and the mole fraction specifically of solvent. So I need to calculate the mole fraction of H2O, and that would be the moles of H2O on top, moles of H2O plus moles of sucrose on the bottom. I'm given grams of each, so I'll need to convert those to moles by figuring out the molar mass. So for sucrose, I'll need my calculator. I've got 12 carbons, so 12 times 12. 22 hydrogens, which is 1 each, and 11 times 16 for my 11 oxygens. And I get 342 for the molar mass. I'll divide to cancel my grams. And I find out that I have 396 divided by 342 is 1.158 moles of sucrose. And then I need to do the same thing for water, except I already know the molar mass of water is just 18, so 624 divided by 18. And that would be 34.67. That'd be my moles of water. So going back to my mole fraction, I would put this 34.67 on top, and then the 34.67 plus 1.158 on the bottom, and put that in my calculator. And I get, it's mostly water, right? You can see that. So it's almost 1, it's high, but 0.9677. Then remember that the equation for vapor pressure is the mole fraction of the solvent times the vapor pressure of the pure solvent, so that'd be the 0.9677 times, and then they gave me in the problem the vapor pressure of water at this temperature, which was 31.8 millimeters of mercury. And so then I would get to 3 sig figs, I would get 30.8 millimeters of mercury. All right. A kinetics problem, I'm looking for the order with respect to F2 and ClO2. So I'm jumping right in here, but really I should start by writing my rate law. So I'm figuring out where F2 is changing and Cl2 is not, but then I want to go plug in and I don't know what I'm actually plugging into. So let me take a second and write the rate law. Rate equals K times F2 to something and Cl2O to something. And so I'm going to do number 3 first. Remember, I like to do the biggest rate first. And so I get 1 times 10 to the minus 3 molarity per second equals K times 0.1 to the X times 0.01 to the Y. And then for number 1, I do 5 times 10 to the minus 4 molarity per second equals K times 0.05 to the X times 0.01 to the Y. So then I'll divide, my units cancel, my K cancels, my 0.01 to the Y cancels. When I divide 1 times 10 to the minus 3 divided by 5 times 10 to the minus 4, I get 2. When I divide 0.1 divided by 0.05, I also get 2, so 2 equals 2 to the x. X must be 1. Now I want to do the same thing where Cl2O is the only thing changing, and it looks like I should look at 1 and 2 for that. Again, I'll do the bigger one on top, so I'll put number 2 first. And again, I'm just going to plug everything in. Divide, units cancel, K cancels, 0.05 to the X cancels, and I get this time 4 equals 4 to the Y, so Y also equals 1. So the question's really saying what is the order? So the order is first order for A, first order for B, and now the overall order would be 1 plus 1, which is second order overall. To figure out the value of K, I need to write my rate law now with those exponents plugged in. So rate equals K times F2 times Cl2O. Solve for K by itself. So I'm dividing F2 and Cl2O on both sides to get K by itself. And then I'm just going to pick one of my experiments and I'm just going to plug in. So I'm picking number 1. So I plug in 5.0 times 10 to the minus 4 molarity per second, 0.05 molar, and 0.010 molar. And then I'm going to put that in my calculator. I don't know if you can see because of the glare. Let me move. There we go. All right, 5 times 10 to the minus 4 divided by 0.05 divided by 0.01, and I just get 1. I do want my answer to be to 2 sig figs probably because most of my data had 2 sig figs. I guess I could go 1. Anyway, 1 or 2 sig figs. It looks like some of the data only has 1. I put 2. And then my units, one of the molarities cancels, and I get 1 molarity in the bottom and 1 seconds in the bottom. All right, looking at a reaction mechanism, I'm looking for intermediates. An intermediate is something that's made in an early step and used up later, so that would be NO3, and that's the only one. A catalyst would be something that I put in an early step and get back later. I don't see any of that. I do see NO2 cancels, but that's a reactant. And then the rate law, I look only at the slow step and I say rate equals K and then whatever happens in that reaction. And there's 2 NO2s bumping into each other, so it's NO2 squared. If I wanted to check that this was the right overall reaction, I just cancel one of the NO2s and I get NO2 plus CO equals NO plus CO2. So that is the correct overall reaction. All right, for this one, this is a short question, but a long problem. So it's a first order reaction, and I'm looking for the half-life. In order to get that, I'm going to have to figure out the K first. I need this integrated rate law. This is the one that we kind of looked at in class, but there was another version of it, which had the concentrations divided. I kind of want that one, so I'm going to just do the math to get that back. So I'm moving the natural log of a sub 0 to the other side by subtracting. Then I can take 2 natural logs that are subtracted and just put them as 1 natural log and divide. So this is the other version, and that will help me a little more. Now in this case, if it's 25% complete, it means the concentration I have left right now is 75% of what I started with, right? 25% has reacted away and 75% is left. And so I can plug those in because I don't know what that number actually is. I can use that to kind of cancel my A sub 0. So right now at A sub t, it's 0.75 times A sub 0. And then A sub 0 is still A sub 0. K, I don't know. 42 minutes is the time I'm interested in. So now those A sub 0s cancel. The natural log of 0.75 is a number that I can put in my calculator. And then this side would just be negative K times 42 minutes. So I can get K by itself by dividing by negative 42 minutes. I didn't put the negative sign, so even though my answer is negative, I know it's actually positive because the negative's canceled. So my K I know now is 0.00685, and the unit would be 1 over minutes or inverse minutes. Okay, we're actually asked for half-life, and remember for first order, it's just the natural log of 2 over K. So that's what I'm going to put in my calculator. So the natural log of 2 is a number divided by the answer I had, which again was positive, but it said negative. So I got negative 101 in my calculator, but that's actually a positive 101. And now the minutes in the denominator of the denominator is just minutes, and it should be a time. It is a half-life. It is how much time it takes for half of the reaction to happen. Okay, a good old crystal structure calculation. I'll start with the mass. So I'm pulling up my periodic table and looking up the mass of vanadium, and it's 40.94. Remember, that's grams per mole. Then I'm going to use Avogadro's number to get that to grams per atom. And then I'm going to use the fact that it's body-centered cubic, and we talked earlier about how that means there's 2 atoms per unit cell to figure out how many grams per unit cell. Or there's 2 atoms per unit cell, that would give me grams per unit cell. So 50.94, I'm just going to multiply across, so multiply by 2, and then divide by everything in the denominator. And then that would be grams per unit cell, because my moles are canceled and my atoms are canceled. All right, for volume, I just need the edge length cubed. It already gave me the edge length in 305 picometers. I do want it to be in centimeters for the next question, so I'm just going to convert it now before I cube it. So 1 times 10 to the 12 picometers is 1 meter, and 100 centimeters is also 1 meter, so that's what I'm using for my conversion factor. And I'll convert it to scientific notation, and I got 3.05 times 10 to the minus 8th centimeters. So my volume is just that cubed. So put in the caret times 3, 2.837 times 10 to the minus 23, and that would be centimeters cubed. So finally, for the density, it's just mass divided by volume. I know my mass is 1.692 times 10 to the minus 22 grams, and my volume is 2.837 times 10 to the minus 23 centimeters cubed. So put that in my calculator. And I got 5.9, I want 3 sig figs, so 5.96 grams per centimeter cubed. And since all of these were actually questions, parts of the question, really all of these should have had 3 sig figs, so let me just go back and round to 3 sig figs. Whoop, 23. There we go. All right, and then finally, what molality of a non-volatile, non-electrolyte solute? All right, this is like what we did in lab, where it tells me how much the boiling point is going to go up by, and the Kb, and it's asking me the molality. So the boiling point went up by 12.5 degrees Celsius. Solve for molality. Divide by 5.95 on both sides. And this degrees Celsius will cancel. I got molality in the denominator of the denominator, so that would just be the numerator. And I got 2.10 molal. There we go. Then it asked me how many moles of solute I would need. It tells me I have 145 grams of the camphor, and that would be the solvent. And so I know that's actually going to have to be in kilograms, so I'm going to convert it right now in my head by just moving the decimal, because I know molality is moles of solute on top and kilograms of solvent on the bottom. So solving for moles of solute, I can just cross multiply and I get molality times kilograms of solvent. The molality I got in part A is 2.10. Remember that little m actually means moles on top, kilograms on the bottom. So times 0.145 kilograms, and I'll get moles. And I have it in scientific notation. I kind of need to, I don't need that in scientific notation. So let me just change it back. 0.305 moles of solute. And that's it. That's the exam. Good luck.